Swayam Prabha. Digital India. Educated India.
Okay, so we had started on boost converter the other day, and I had just written the basic configuration of the boost converter. We have still not drawn the waveforms. So I said basically you are going to have a V in, and then you are going to have an inductor which is trying to store energy when I have this particular switch S being closed. So when the switch is closed, if you assume it's ideal switch and ideal inductor, the entire energy, that is the voltage that is being applied, is going towards increasing the current in the inductor. So I will have during T on interval, I am going to have V in equal to L di, that is I can write this as dt, right, divided by L delta I divided by dt, right. This is going to be the equation as far as the on time is concerned. Now after this, you are going to have actually a diode connected like this and a capacitor connected in this particular direction, and I am going to have a load connected here, and we are going to have actually the inductance stored energy which is actually being released during off interval. Its voltage comes in series with the voltage that is input. So V in plus whatever is VL, both of them come together in series addition, because of which V0 actually is a large value. So we are going to have V0 greater than V in because of the inductance stored energy. So during T off, if I write the equation, I should have actually, during this particular interval, I am going to have the inductance during the off interval. I am going to have the inductance having minus here and plus here. This is going to be the case during off interval. That is when I am going to have a switch off. Whereas when the switch is on, I am going to have it the other way round. I am going to have this as plus and this as minus when the switch is on. Right? So we are going to have during off interval, we are going to have L delta I divided by 1 minus D times T is going to be equal to whatever is the difference between V in and V0. So if I write it like this, I should write this as minus delta I because the current is decreasing, or I can write it the other way around, saying that L delta I magnitude is equal to, so I can simply write L delta I magnitude is equal to V0 minus V in, because V0 is higher, 1 minus D times T. Similarly here I can write L delta I is equal to V in dt, and we equated these two. Right? That's what we did, because the increase in the inductor current has to be equal to the reduction in the inductor current. So we can say basically that V0 equal to V in divided by, I think, 1 minus D. This is what we got as the expression by using these two. So if I call this as equation 1 and this as equation 2, so from 1 and 2, I should be able to write it like this. Right? This is what is actually the expression for this particular input-output relationship. Let's try to now draw the waveforms. I am trying to draw the waveforms for this particular convert. Okay? We started off with inductor current, if you may recall. So let me draw this as T. So we had the inductor current increasing and maybe decreasing and again increasing, decreasing, again increasing, decreasing and so on. This is the way the inductor current was. Okay, there was a question from one of your classmates why we are taking this current as linear. One is we are neglecting whatever is the resistance that is coming along with the inductance, and second thing is the rate at which the inductance is being switched on and switched off. The switch is being switched on and switched off is very much higher as compared to the time constant. So for a small short time period we can assume it to be fairly linear. So that is the reason why we are assuming it to be linear, because the switching frequency is normally assumed to be much higher than the time constant of the inductance itself. So it will definitely not reach a constant value eventually. We will not allow it to reach a constant value. It's still increasing, and that too linearly. That's what we are trying to say. So I'll have to draw this time interval. So this is going to be one of the time intervals which is corresponding to, say, dt, right? And the next one is going to be corresponding to the end of the period t, right? So this is actually my IL value, and it is starting from whatever is my I minimum and reaching I max. So I can say this is actually my delta IL value until here. This is delta IL value, right? Now if I look at the inductance voltage during this interval, right? When I am actually turning it on, the switch is turned on, V in, whatever is the input voltage that is coming across the inductance. So during the on interval, I should show it as though I am going to have V in. If I say this is V in, so I am talking about what is the value of VL. VL waveform I am drawing. So this is V in. And when I am looking at actually the off interval, I will have whatever is V0 minus V in the reverse direction. So that is the reason why we are drawing it in the negative direction. So this is going to be, say, V0 minus V in magnitude. V0 minus V in magnitude. That is coming as the inductance voltage during the off interval. Very clearly, if I call this as A1, area 1, and this as area 2, A1 and A2 have to be equal to each other, because the inductance cannot retain any of its energy for the entire cycle. Whatever it is taking, it has to come back to its original state at the end of that one cycle. So if I actually look at this area, so again if I just try to draw this entire thing again for the second cycle as well. So this is corresponding to on interval and this is the off interval. So I am going to have again this as, say, A1, and A2 has to be exactly equal to A1. So A1 and A2 have to be equal to each other so that the inductance does not retain any energy. So we are talking about again steady state operation. Like what I said, I am not taking as though the circuit was completely dead and I have turned it on, because if I do that, definitely inductance will take a while before it accumulates some energy, right? So this is going to be the waveform for inductance voltage. Now let us try to take a look at what is the kind of input current that I am going to have. Please note that now the inductance is connected on the input side, just like how it was connected on the output side as far as buck converter was concerned. So whatever was IL average in the buck converter, it was I0. Whereas here IL average is going to be I in, whatever is the input current. So if I try to look at what is the average current here, maybe somewhere here, this is the average value. This is going to be I in average, which is also same as IL average. So IN average and IL average are essentially one and the same. But if I look at what is the load current, right? The load current is essentially whatever is the current that is flowing through the resistor. Very clearly during the on interval, the supply has nothing to do with the load, because it is essentially being short circuited through the inductance with this switch. There is no question of the supply getting connected to the load at all. So if the capacitance is having some stored energy, that is going to retain the load current. Whereas if I try to look at the off interval, the inductance is actually driving the current through the diode, and it is going to actually drive the current through both these. The capacitance, whatever it had lost during the on interval of the switch, it will try to replenish during the off interval of the switch, because the inductance stored energy is coming to the load. Along with that, the capacitance is also getting some amount of the stored energy. So the capacitance is going to get, charged during that particular interval. So if I say this is T, again if I try to draw what is the diode current, diode will not have any current during off interval. So during on interval, whatever is my inductance current, that is going to come up as the diode current. So I should say this is what is the diode current. This is going to be the diode current. So the diode current comes up only during the off interval of this entire cycle. If I try to look at it for one cycle, only during the off interval I will get the diode current. And if I look at the diode current's average, that is if I try to average it, then I'm going to get something like this as the average. Probably, this is going to be the average, probably. And this average is actually I0. Right? Because whether I like it or not, the load current has to continue. We are assuming that the load has to be supplied continuously, and we are assuming output voltage is V0. So I need to get continuous current in the load, and that is essentially being made possible by the capacitance stored energy. So the capacitance is going to give the current during the off interval, and otherwise it is going to, during the on interval, and otherwise the inductance is going to release its stored energy. So if this is I0 and this is diode current, I can write here ID equal to IC plus I0. Right? So because of which I should be able to write clearly what is the capacitance current. So I can write that I can draw that the capacitance current is somewhat like this. I'm going to get some portion like this, which is probably the diode current, and some portion like this, which is I0. So this is actually ID minus I0. This is ID minus I0. So I will have this repeating cycle after cycle, right? So I'm going to have something like this, and then again something like this as my IC. If I try to draw, this is ID. What I have drawn here is the diode current, right? So this particular portion is what is actually given out by the capacitor, whereas this is what is gained by the capacitor. So I should say this is delta Q, which is actually capacitor getting charged, right? Whereas this is delta Q, where C is discharged, or it is getting discharged through the load. So I should have these two equal to each other, right? Because the capacitor, if I have some net charging or net discharging, the voltage will keep on going down, or it will have increase in the voltage. So if I assume that the voltage is fairly a constant, this delta Q has to be equal to whatever it has gained, it should be giving back also, right? So whenever it is gaining, if I try to look at what is the kind of capacitance voltage, so the capacitance voltage should be increasing whenever it is gaining charge, and it should be decreasing whenever it is giving back the charge. This is how it should be. So this will be whatever is my VC value. Right? So the capacitance voltage will essentially increase and decrease, but we want that to be within the limit, whatever we are specifying, and that is how we design the capacitor value. Right? We arrive at the capacitor value. So first of all, to arrive at what is the minimum value of inductance to maintain continuous current, right? Continuous inductor current. So let us try to look at first of all critical conduction mode. So let us say I am decreasing the inductance further and further. Clearly, I am going to have more and more ripple in the current. So the current ripple might increase, and maybe I will have a waveform something like this. It may go from here and reach very high value here and come down, and then again go from here, reach very high value and come down. So this is essentially showing the case where the inductance has been decreased quite a bit. Right? Under what condition I am going to have that just touching zero value. Right? So this is actually going to, so I will have delta IL by 2 is equal to IL average under this condition. And IL average we already said is also I in average. This is also same as I in average. And we know that if it is a lossless converter, I can write V in I in equal to V naught I naught. So I can simply write V naught equal to, rather I naught equal to V in I in by V naught. So V naught I can write this as V in by 1 minus D. So I can simply say 1 minus D times I in is equal to I naught. 1 minus D times I in equal to I naught. So I can write this IL average as I naught divided by 1 minus D. Right? I can write this as I naught divided by 1 minus D. Now, here I should be able to write this as V naught divided by R into 1 minus D. Because I naught is same as V naught by R. So V naught by R into 1 minus D. And delta IL, let us try to substitute the expression. This is one of the easier ones. So let us just put this here, which is actually V in dt divided by, this is delta IL, I am writing the expression. So V in dt divided by 2L. This is equal to delta IL by 2. This is same as delta IL by 2. So I am just equating these two. That's all. So I can, let me just put again V in, I can write this as V naught into 1 minus D. So I can write V naught into 1 minus D multiplied by dt divided by 2L. Right? Now let me just equate these two. That's it. These two expressions, V naught and V naught I can cancel. So I should be able to write this as R 1 minus D whole square multiplied by dt. Right? Okay. So let me just write that. So it should be 1 minus D whole square multiplied by D, right, multiplied by R divided by 2F. So this is the expression for the minimum inductance for maintaining critical conduction or continuous conduction. Just continuous conduction. What I mean is the current will just touch 0 and then it will go from there, again it will increase. Right? So if the inductance has to be, the inductance happens to be greater than this value, it will be continuous conduction. If the inductance happens to be lower than this value, it is going to be discontinuous conduction. Right? Now, if this is all for this particular duty ratio, this particular resistance, right? And also for a particular frequency. So if I increase the operating frequency, my inductance can come down. So higher the operating frequency, again smaller the inductance, same as what we talked about in the case of buck converter. Now we are yet to arrive at capacitor value. We have to arrive at the capacitor value. So whatever we actually drew as the waveform corresponding to capacitance current, we can try to get the expression for delta Q. Clearly, getting this delta Q is easier, right? Because I have a rectangular area, so it's much easier. So if I try to get the area of this particular delta Q, it is actually I naught is the value, and what is the time duration? Time duration corresponds to on time. So it is dt, right? So I should say I naught multiplied by dt is equal to delta Q for the capacitor. Right? So I can write this as C multiplied by delta V naught, whatever is the ripple in the voltage. Right? So I can write this I naught as V naught by R. Right? So I can write this as V naught by R dt equal to C delta V naught. So I can write delta V naught by V naught equal to D divided by RCF. Right? Okay? So this actually is giving me whatever is the capacitor design for arriving at a particular value of voltage ripple. The voltage ripple has to be within that particular value. So then you will be able to get this. Right? So in the case of boost converter, one of the limitations what we have, as I mentioned in the last class, is the inductance value to which I can design it. So in most of the cases where it is a very high power system, large power configuration, it becomes extremely difficult first of all to design an inductance value corresponding to very large current as well as a larger value. Please understand, if I want the inductance value to be larger, you guys must recall what you studied in magnetic circuit. L will be generally number of turns square divided by the reluctance R. Right? So if I want the inductance to increase in its value, I have to have a large number of turns. If I have a larger number of turns, I'm going to get a good inductance value. And reluctance has to be smaller. That is what it is. So normally we use iron core inductors. But iron core inductors can result in very high hysteresis loss, especially if I am talking about high frequency of operation. Then, you know, any amount of hysteresis loss you get will be actually whatever is the area under the curve, BH loop multiplied by the frequency. So if I work on higher and higher frequency, there will be extremely large hysteresis loss. So generally for high frequency inductors, we do not use iron core. We tend to use ferrite core or some kind of amorphous core. So there will be filings of iron which will be filled inside, you know, probably a non-conducting material, and then that will be used as the core. So those are generally known as powdered iron or, you know, kind of filings of iron. which will be actually not having any proper BH loop, because every ion acts like a separate, entity there. So that is the reason why you may not have a large amount of hysteresis loss. So normally we use something like this, and there will be definitely more amount of air gap. You should understand that when I use ion filings, there will be definitely more amount of air gap. So you would normally see that the leakage could be somewhat larger. So high frequency inductors will normally have larger amount of leakage, and you will normally see that they are not made up of solid ion material, because to avert the hysteresis losses. That's the reason, right? So if I am talking about a large power capacity boost converter, first of all, the number of turns have to be larger, I told you, which means I have to have thick conductors also. High power means it will carry larger current. Thick conductors making multiple number of turns around an amorphous core is not easy, because it may not have the mechanical strength, right? So generally boost converters, especially in high power capacity, have a limitation of about stepping up of 2 to 2.5 times, generally not more than that. Very rarely we see much higher capacity of boosting up of the voltage generally. So it has a limitation because of the inductance itself. So inductance is generally a big headache in any of the converters normally. And in boost converter it becomes a must. Because buck converter, if I am using it with a motor, in all probability I may not even include an inductance explicitly. The motor inductance itself is sufficient enough normally. So I may not even include any explicit inductance. So let us try to now go to the third type of converter, which is actually a buck boost converter.